Every now and then a scientific paper comes along that's so ambitious, so out there, it just makes you stop and go, whoa. Today we're diving into one of those. It's called the Coherence Field, and it's basically a single mathematical framework that claims to describe how order pops up in, well, pretty much everything. We're talking project teams, a piece of music, even consciousness itself. Okay, let's get into it. And right away, this isn't your typical stuffy academic paper. I mean, the preface opens with this line. It sets a tone that's both incredibly human and, at the same time, super rigorous with its math. It's such a bold statement, isn't it? It's all about building a bridge between the hard numbers that run the universe and the actual meaning we find in our lives. So, here's our game plan. First, we're going to unpack the big idea, a single formula for order. Then, we'll get our hands dirty and actually deconstruct the core equation. After that, we'll see how it can chase goals without causing chaos, check out some real-world examples, and then land on the most important part. How can we actually test this thing to see if it's for real? Okay, so the central idea behind the coherence field is pretty simple at its core. All the order we see around us, a team just clicking and hitting a deadline, or a musician playing something beautiful, it's not an accident. The paper argues that it all stems from the same set of rules, these field-like dynamics that can be described by one single, unified law. Now, this is what I think is so cool. The authors put a huge emphasis on that word, falsifiable. See, this isn't just some vague philosophical concept. They've built this entire thing from the ground up to be tested. They're basically saying, here are our predictions. If they don't match up with reality, then the theory is wrong. That right there is the heart of real science. So let's get to the main event. This is the core equation, the engine of the whole framework. The paper calls it the Genesis ODE, which stands for Ordinary Differential Equation. Now, I know it looks a little intimidating, but it's really just telling a story. It's a story about a constant tug-of-war between the forces that build things up and the forces that tear them down. And this diagram shows you all the players in that story. Think of each of these boxes as a character. Each one represents a different force that's pushing or pulling on the system's overall health. Some are driving it forward, trying to achieve a goal, while others are dragging it back, trying to pull it all apart. So it all comes down to this incredible balancing act. On one side, you've got your forces for order. Homeostasis is the system's instinct to just stay stable and not fall apart. Teleology is that forward push toward a goal. And coupling is all about how well the different parts are working together. But on the other side, you have the forces of disorder. Entropy is that natural tendency for everything to just kind of decay over time, and effective drag is all the real-world friction. Deadlines, pressure, you name it. And all of those forces, that whole tug-of-war, boils down to one final score. It's called coherence, and it's represented by the letter C. Think of it like the system's pulse or its health bar. It's just a number, from 0 to 1, that tells you in a single glance how well things are going. A high C means you're in a state of flow. Everything's working. A low C means you're heading toward chaos. Okay, this brings up a really important question. If you build a system that's super driven to reach goal, how do you stop it from just going haywire and spiraling out of control? Well, the framework has a really clever answer for that. It's called the teleology cap. Just look at this graph. That yellow line, that's a runaway system. The drive to get to the goal just gets stronger and stronger, which is super unstable. But the blue line, that's the system with the cap. The drive pushes hard towards the goal, but then it smartly levels off. It gives you all that power, but with control. It's basically a mathematical safety brake built right into the physics of the system. And the safety features don't stop with the math. The framework actually calls for a dedicated ethics and governance layer. This thing acts like a supervisor that can literally hit pause or even stop an action until certain safety checks are passed. It just goes to show that for these researchers, ethical behavior isn't some afterthought. It's a fundamental part of the design. All right, so we've got the theory, but what about the real world? This is where you can really see just how flexible this framework is. Let's take a look at two totally different examples. So first, think about an organization. Here, the coherence score, C, could track how well a project is getting done. The equation would model the project goal, how aligned the team is, and the drag from things like deadlines. But then, and this is wild, you can take the exact same equation and use it to model a musician. Now coherence measures musical harmony. The goal is to create beautiful sounds, all based on the actual physics of acoustics. And we're not just talking in metaphors here. The paper dives deep into the musician example, grounding it in a specific tuning system, the 432 Hz standard. This just shows you how deep the framework goes. It connects the abstract math to real, tangible, physical properties of our world. Okay, so let's circle back to what makes this whole thing so scientifically powerful. Its dedication to being provably wrong. The authors even dedicate the paper to Stephen Hawking for this very reason. The entire framework is built to be tested. So how do we actually do that? I mean, a beautiful equation is one thing, but does it make real predictions about the world that we can go out and measure? Well, the answer is a big fat yes. Here's the first big test. The model makes a very specific and kind of counterintuitive prediction. It says that for any system, the best performance, the peak synergy, doesn't happen when all the parts are connected as much as possible. Instead, there's a sweet spot right in the middle. Too little connection and nothing gets done, but too much connection and the system gets too rigid, too slow. This inverted U shape is a clear, testable prediction. And get this, here's another test, one that tries to measure creativity itself. It's a bit complex, but using this powerful math technique, the framework creates these things that look like barcodes. The simple way to think about it is that each long bar represents a stable idea or structure in the system. When a genuinely new, lasting idea emerges, a real creative leap, a whole new long bar appears on the chart. It gives us a visual way to actually count and measure innovation. How cool is that? So the whole point here is this deep, deep commitment to the scientific method. The paper literally has a section called the Falsifiability box, where it lays out the exact conditions that would prove the theory wrong. This isn't dogma. This is a confident, open invitation to the entire scientific community, saying, hey, come try and break this. And that all leaves us with one final massive question. If this framework actually holds up under testing, could it be more than just a cool way to describe the world? Could it be a blueprint, a user's manual for actually building better systems? More harmonious teams, safer AI, more effective organizations. The potential is just staggering, and it feels like we're watching the very first steps of a brand new scientific journey.